hot water going out, and it's circulating through here. And so hot air coming out of there goes through this refrigerator and blows out cold. So you don't have any hot aisles anymore. Everything is cold. So now the cooling is right where the heat is generated. It's much more efficient.
I'm at a supercomputer.
So this is tying all the computers together. It's tying into the disk systems. So here's one of the disk systems. This holds about 3 petabytes. So that user that wanted 3 petabytes, they can build up this entire set of disks. So there's the visualization. That's the fourth part. So the computing, the networking, disk storage, and visualization or data analysis are all critical parts of that. This looks pretty nice. You can see labels on every single wire. You need to know where it is going and where it's coming from. If you have a problem on a wire, you need to know which one to replace. Because you're not going to go through 100,000 wires and test each one to figure it out. So we label every one, and we have it very, very tightly laid out to where it comes from, where it goes to, and how it gets routed. I'll show you a little more of that over here. So this is an example. You know, we've got these bundled just so. We run them in trays under the floor, so this floor is 2 feet above the concrete, and that's where the air used to flow. Not much air is flowing there now. But we have these trays, these runners of cables that go out onto the floor and spread out and go down each aisle to connect all those systems up to this hub and then up to the other. Comes into the facility through these power panels. There's probably a third of a megawatt running through here. Take off that panel down there, you can see these huge cables that are sending power out to these guys. And each of these is an 8 megawatt, which sends power then, conditions the power and sends it out to the racks here. These racks are sort of getting higher and higher power. Each one is 20 kilowatts. That's sort of been going up over time. And so it's taking more of these things to power the racks. A little over 100 teraflops, so it adds about 10% to the capacity of Pleiades. And they're in the process of installing those now. Once all the testing gets done, all of this gets bundled up and much needed so that you can troubleshoot what you need to. Until very recently, just a couple of years ago, this computation was just too hard to do. Folks didn't know how to put Einstein's equations of general relativity on computers and actually allow black holes, which are doing all kinds of naughty things to the space around them. How do you turn that into a set of equations that doesn't sort of blow up or become unphysical? How do you do that? And so recently they figured out how to do that. Now they can orbit black holes and actually have them spiral into each other, merge. And this equation, this simulation predicts what the gravitational radiation would look like from a merger like that. And NASA and other agencies and countries are actually developing experiments and running experiments to try to measure and observe those gravitational radiation bursts. So now we know what to look for based on these models. Very little variation. It's just a mist kind of. But there are little variations, and those places where the density of matter was denser, was higher, it sort of collapsed and formed these big clusters here, big knots of matter. This is actually dark matter that we're showing, not regular matter like our galaxies. You and I are made up of dark matter, which sort of surrounds galaxies. So if I look at a big clump like this may have 100 or 1,000 galaxies sort of gravitationally bound inside that come up with dark matter. We can't see it, it doesn't interact with us, but we can model how it works and see if our understanding of regular matter and dark matter match what we see. And statistically, so this model is identical to what we see in Hubble. You can see these strings, these sort of filaments and bubbles where inside there's very little matter, and all equations 1/16th degree apart, 360 degrees around the Earth. That's about, say, 5,000 points in the horizontal direction and a similar number of points in the vertical direction. So we've divided the Earth up into about 25 million little points where we solve the equations of motion for the ocean. But it's also, you have to, since we're doing an ocean model, you have to divide the vertical direction as well. So there's about 100 levels in the ocean. So now we're up to 2.5 billion potentially points where the equations of this ocean model are solved. So super high resolution, it takes a supercomputer to do this. This computation here is to test the accuracy of our modeling code, our simulation software. So we had a lot of data about pressures and temperatures and airflow during that launch, and we're comparing to what the simulated models tell us. That's very important to do, because how are you going to know if you're doing fewer and fewer experiments? How are you going to know whether what the simulation codes, what this software is telling you is true? Well, we need to compare it to some experimental cases in order to have confidence. There are other ways to do it, but this is a primary way to test the accuracy of your models. So we did this, and it showed that there is very high correlation, very good accuracy of this particular modeling code. And we zoom in a little bit more. I think there are 400 million stars in this picture, which is just a small fraction of the number of stars in our galaxy. A huge amount of, tons of things going on. You can see, remnants of supernova. In the center of these things, this red area is gas that's been blown out from a supernova, and then the green represents dust. Sorry, I think that's backwards. The dust is heavier, it doesn't get blown out quite as far, and the green areas are gas, which gets blown out further. And there are all different shapes which are described by that name up top. I don't know what necessarily what all those mean. These are at different speeds if that vehicle were launched. So during its launch trajectory, it's getting up to thinner atmosphere, we're going higher speeds. And so this data set is actually larger than the wall. You can go down to higher speeds. So that goes up to Mach 3, goes down to Mach 0.6. So now we can look at a huge step ground vertically. So this is just looking at the propeller part of that aircraft and how, in fairly good detail. We've done actually much higher simulations. I should probably put those into this presentation. There are two which are in hover mode. They're just going straight up or hovering at a single distance. And then there are two that are in forward motion. At some point, we'll reach a maximum pressure on the vehicle. I believe that's where this point is. It's colored by the pressure on the surface of the vehicle. And if you can see, if you have good eyes or you want to come up and look at this, you can actually see a comb of the airflow over that surface up on Mars. And so over at JPL, they've taken and stitched all these pictures, this panorama of images together. You can see the seams a little bit, some of these.